Have you ever wondered how electrons are distributed in an atom? Well, it all comes down to the quantum mechanical model. This model tells us that the behavior of electrons can be described by something called a wave equation. Think of it like the equations used to describe waves in water. When we solve this wave equation, we get what's known as a wave function or orbital. This wave function is represented by the Greek letter psi or pu. By plotting the square of the wave function in three-dimensional space, we can visualize an orbital. Think of an orbital as a blurry photograph of an electron, captured at a slow shutter speed. This photo shows the volume of space around a nucleus, where the electron is most likely to be found. The orbital appears as a cloud, indicating where the electron has been, rather than a sharp boundary. For practical purposes, we define this cloud as the area where the electron spends 90% to 95% of its time. So, when you think of orbitals, imagine that hazy, dynamic space of possibility. What do orbitals look like? There are four types: S, P, D, and F, each with unique shapes. Today, let's focus on S and P orbitals, the stars of organic and biological chemistry. An S orbital is spherical, with the nucleus right at its center. In contrast, a P orbital has a distinct dumbbell shape. Now, let's talk about D orbitals. Four of them are cloverleaf shaped. The fifth D orbital, it's like an elongated dumbbell with a donut around its middle. These shapes are crucial for understanding how atoms bond and interact. Let's dive into the fascinating world of atomic structure. In an atom, orbitals are organized into different electron shells around the nucleus. Each shell has a larger size and energy level than the one before it. The first shell has just one s orbital, called 1s, holding only 2 electrons. Moving to the second shell, we find one 2s orbital and 3 2p orbitals, totaling 8 electrons. The third shell is even more complex, with a 3s orbital, 3 3p orbitals, and 5 3d orbitals. This allows for a total capacity of 18 electrons in the third shell. These groupings of orbitals help define the energy levels of an atom. Let's dive into the fascinating world of p orbitals. In each shell, there are 3 p orbitals: px, pi, and pz's. These orbitals are oriented in space along mutually perpendicular directions. Each p orbital has 2 lobes, separated by a region of 0 electron density called a node. This node is crucial because it indicates where the probability of finding an electron is 0. Interestingly, the lobes have different algebraic signs in their wave functions, represented by different colors. These signs play a significant role in chemical bonding and reactivity. Understanding this can really change how we think about molecules.